So here is figure 2. So here is my transmitter. Here is my receiver. Let's say these are both fixed antennas, not moving. There's a direct path from transmitter to receiver. And we'll call that distance D1. And there's also a bus right here, moving this way at a velocity. And there is a path reflecting off the back of the bus and back towards my receiving antenna, like so. Call this D2. Yes?
Generally, we do this properly. We look at two signals. We'll say, okay, well, there's the direct path, and there's some other path, like for instance, off this bus. But in the case, like in reality, there's many, many other paths. How does this come into the calculation?
So, I mean, this is a very clean scenario that I can solve on the board. If we had dozens of paths,
like 3, 4, let's say.
sure. I mean, 3 or 4. You could probably, I mean, ultimately, if you have 100 paths, or if you have n paths, you can probably solve it in closed form. You can look up all the trig and then write it all down. My intention in presenting these two-path examples is to illustrate, basically illustrate examples. So in reality, you don't have nice, clean situations where you know that you're exactly D1 away from the transmitter, and the reflector is distance D2 or something like that. Generally, what I'm doing here is I'm illustrating that these kinds of effects can occur, and so you have to plan for them. So basically, you'll have some idea as to why fading occurs, why it's bad, and what you need to do to overcome it, which is generally just boost the available power. So in this case, the received signal is this will be equation 6. I skipped an equation, so there's a little error in the notes. I skipped an equation number. Direct path is sine 2 pi c t plus d1 over c. Plus sine 2 pi c t plus the initial distance, d2 over c, plus the changing distance. So this guy is retreating from the receiving antenna at a velocity of d. So this, let's just call this a one-dimensional model, so everything's sort of in the same direction. And here I would say plus, okay, would I say v2 t over c? Would that be correct? So if this guy moves 10 meters down that way, does this path lengthen by 10 meters?
So if it's perfect straight.
No, it doesn't.
No, twice that.
Twice that, because it has to go and come back. So it's actually 2 v2c t over c, just in the context of this specific example.
You're assuming it goes back to the first antenna, but it doesn't. So like, it goes there and comes back to the second antenna, so that's not double the distance. That's actually double.
No, I'm talking about not double the distance, but double the change in distance. So if, for instance, if this guy moves 10 meters this way, then I have to cover D2 plus the 10 meters here and the 10 meters back. So it's double the change in distance. And using using my trig identities from before, this is equal to 2 sine, 2 cos d1 minus, 2 cos phi fc d1 minus d2 over c minus v2t over c plus v2t over c. No. Minus v2t over c times sine 2 pi ft plus d1 plus d2 over 2c plus v2t over 2c. So what do we see from this expression? Here is my signal term, and there's my Doppler frequency. There's my increase in frequency from the Doppler. But also, the this is the fading term. The fading, the term under this fading is now a function of t. So with a frequency of FCV2 over C, this this fading term will cycle. Yes.
Is that a minus d1 minus d2?
D1 minus d2 over C minus v2 over C. And you can get this from the same trig identity that we've done for all of these two path pieces. Questions on that? Okay. For example, if FC is equal to 1 gigahertz, the D1 is equal to 100 meters, D2 is equal to 100 meters initially, but B is equal to 27 kilometers an hour. And I chose that number specifically because that's equal to